Welcome to the coupled RLC circuit video. In exercise 1, we'll be measuring the natural frequencies of the two RLC circuits.
First, we'll set up the RLC circuit. Use a T-connector on the function generator so that we can view its output on the oscilloscope as well as send it to the circuit. Using a BNC to banana adapter, connect one pin to the inductor. Connect the other end of the inductor to the resistance box. Connect the other end of the T-connector to the oscilloscope. Use the second BNC to banana adapter on channel 2 of the oscilloscope. Connect the ground pin, the metal one, to the ground pin of the function generator. Note that your circuit will not function properly if this order isn't adhered to. Connect the capacitor to the other function generator terminal. Connect the other oscilloscope pin to the remaining terminal of the resistance box and add the other capacitor wire here to complete the circuit.
Next, we'll verify that our circuit is working properly. Begin by adjusting the oscilloscope channel levels and timescale so that you can see a signal. Ensure that the function generator is putting out a square wave at a frequency significantly lower than the natural frequency of your circuit. If all goes well, you should see an oscillatory signal that is high in amplitude when the square wave switches, but rapidly decays.
Add a wire to short out the resistance box. Ensure that your oscilloscope channel levels and timescale are set appropriately. Insert your USB drive and press recall/save. Ensure that action is set to save all and press the save button. Note that these oscilloscopes will take some time to save your data.
Remove the oscilloscope from the capacitor and the function generator from the circuit. Make sure to reattach the inductor, resistor, and capacitor in series for future use. Replace the entire circuit with the second RLC circuit. Add the oscilloscope across the capacitor and break the circuit to add the function generator.
Short circuit the resistance box and measure the natural frequency of the circuit as before.
In exercise 2, we'll be constructing an amplitude spectrum of the coupled RLC circuit and recording the normal frequencies and the frequency giving a minimal amplitude in the coupled capacitor as a function of inductor separation. Remove the wire shorting the resistance box and choose a resistance to work with. If using Data Studio, make sure the voltage doesn't saturate at resonance.
Bring the other circuit back and place the inductors next to each other for maximum coupling. You may need to zoom in on the capacitor's decaying oscillations to see the effect of coupling the inductors together.
Change the function generator to output a sine wave. Disable the display of the original signal and sweep through a wide range of frequencies. This will allow you to find one of the normal modes and thus establish the general frequency range in which to record.
If you choose to use the oscilloscope to measure amplitudes, remove the BNC cables from channel 1. Replace it with the BNC to banana adapter and connect banana cables across the coupled circuit's capacitor. Re-enable the channel 1 display. You can now measure amplitudes by pressing measure and using two of the available slots for channel 1 peak to peak and channel 2 peak to peak.
Set the function generator to a frequency below both resonances. Record the amplitudes, increase the frequency, and repeat until you've established complete amplitude spectra for both capacitors. Note that you should gather more points near and between the resonances. Also note that if the signal goes off-screen, the oscilloscope will display an unreliable value with a question mark, and you should adjust the scale.
Separate the two inductors, say by 1 centimeter. Set the oscilloscope to display only the coupled capacitor, which can conveniently be used to find all three relevant frequencies. Vary the frequency to find the two maxima and the local minimum between them. Record all three frequencies. Increase the inductor separation and repeat. Do this until you have a reasonable plot of each of these frequencies as a function of inductor separation.
Why won't Heisenberg's operators live in the suburbs? They don't commute.